Assalamualaikum warahmatullahi wabarakatuh. Today we are going to present to you about the group 15 and group 16 element. First of all, we are going to discuss about the group 15 element. So, the properties and application of group 15 elements. First, my name is Nur Akila Uzma binti Nur Hisam with matrix number 207685. My friend Nur Ayuni Zahira binti Muhammad Radwan with matrix number 207656, and lastly my friend Nurul Farhanis binti Zulkifli with matrix number 207688 will first present to you about the group 15 elements. So, the group 15 includes the nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. So nitrogen and phosphorus are known as non-metal, while arsenic and antimony are known as metalloids, while lastly bismuth is known as a typical metal. So the valence electronic configuration of these elements is Ns2 and P3. So the s orbital is completely filled and the p orbitals are half filled, which making the electronic configuration extra stable. So later we are going to discuss details about this group 15 elements. So the basic strengths of atomic properties. Firstly, we have atomic radii. As we know, as we moving down the group of group 15 elements, the ionic radii and the atomic radii increases. Why? This is due to the expansion of another main energy level in each progressive element. So, next we have ionization enthalpy. Group 15 has higher values of ionization enthalpy than group 14. This is due to the higher atomic charge, smaller nuclear radii, and stable half-filled electronic setups. As we go down the group 15, the ionization enthalpy values become diminished. This is due to the progressive increment in the nuclear size. So, then we also have the electronegativity. The electronegativity is the inclination of a particle to pull in a shared pair of electrons more towards itself. The electronegativity diminishes bit by bit on moving down the group because of the increases in atomic radius. So here I want to share some that electronegativity also can consider which bond that the elements is. So first, for example, we have the CL2 molecule, which when it has a lower difference in electronegativity, so it will consider as non-polar covalent bond, which is the electrons are shared equally. So next for the HCl, it will have a difference in electronegativity in the middle, which is not too high and not too low, and it is considered as a polar covalent bonding, which is the electrons are shared unequally. So lastly, we have NaCl. So NaCl have higher difference in electronegativity, which is considered as ionic bonding, which electrons are completely transferred. So that's all from my part. I will pass to my friend. Thank you.
Hi, my name is Nur Ayuni Zahira binti Muhammad Radwan. My matric number is 207656. I will explain about physical properties in group 15. So, physical properties incorporate physical state, boiling point and melting point, metallic character, density, and allotropy. So, nitrogen is a diatomic gas, while the rest of the elements in group 15 are solids in nature. For boiling point, the boiling point increases from nitrogen to bismuth. For melting point, first the melting point increases from nitrogen to arsenic because of the continuous increment in nuclear size. The low melting point of nitrogen is because of its discrete diatomic particle, while the high melting point of arsenic is described to its Gaussian layer structure in which the layers are firmly pressed. Next, the fact that the nuclear size increment from arsenic to antimony, there is a decrease in their melting points. Despite the fact that antimony has a layered structure, it has a low melting point than arsenic on account of the generally free pressing of particles. Lastly, the melting point of bismuth is not as much as antimony. The packing of atoms loosely by metallic holding. So, next for allotropy. Allotropy is the existence of a chemical element in two or more forms which may differ in the arrangement of atoms in crystalline solids or in the occurrence of molecules that contain different number of atoms. So all group 15 elements, aside from bismuth, indicate allotropy. Nitrogen is found in two allotropic structures, that is alpha nitrogen and beta nitrogen. For alpha nitrogen, it has cubic crystalline form structure, while beta nitrogen, it has hexagonal crystalline structure. For phosphorus exists in numerous allotropic structure, which is white phosphorus, red phosphorus, and black phosphorus. For white phosphorus, it is volatile waxy white solid, which is dangerously reactive in air, and it glows with a white light and spontaneously bursts into flame. For red phosphorus, it non-reactive with air at 25 degrees Celsius. It has a 190 degrees Celsius of melting point. Lastly, for black phosphorus, it non-reactive with air at 25 degrees Celsius. For arsenic and antimony, arsenic exists in three essential allotropic structures, which is black, gray, and yellow. For antimony, it has three allotropic structures. To be specific, it is yellow, metallic, and explosive. Other physical properties in group 15 is metallic character and density. Moving down a group, metallic character increments with an increase in their nuclear size. The density of this group 15 element increased from nitrogen to bismuth. Next, I will go into oxidation state. Every of the element group 15 has 5 electrons in their outermost shell. They require just 3 electrons to finish their octet setup. The octet can be accomplished either by picking up 3 electrons or by sharing 3 electrons by a method for covalent bonds. Accordingly, the basic negative oxidation state of this element is -3. Moving down the group, the propensity to display -3 oxidation state diminishes. This is because of the expansion in nuclear size and metallic character. Group 15 elements additionally indicate positive oxidation state of +3 and +5 by developing covalent bond. Because of the inner pair effect, the +5 oxidation state stability diminishes down the group, while that of +3 oxidation state increment. Nitrogen has just s and p orbital, yet no d orbitals in its valence shell. Therefore, nitrogen can demonstrate a most extreme covalency of 4. A covalency of 4 is reached by the sharing of its lone pair or electron to another iota or particle. So this is the oxidation state for group 15 element, which is for nitrogen, phosphorus, arsenic, antimony, and bismuth. So that's all for me.
My name is Nurul Fahanis binti Zulkifli and my matric number is 207688. So today I'm going to continue with the anomalous properties of group 15 element. So what is anomalous? Anomalous of an element refer to the deviation of the properties and behavior of an element from its usual or normal behavior. So, nitrogen differ from the rest of the element in the group 15 due to its small size, high ionization enthalpy, absence of the orbitals, and also high electronegativity. Some of the anomalies observed are nitrogen exists as diatomic gas. This can be explained on the basis unique tendency of nitrogen to form extremely stable pi-pi multiple bond with itself because of the effective lateral overlap of small 2p atomic orbitals. Nitrogen also can form stable pi-pi multiple bond with carbon and also oxygen, whereas the other element in group 15, they do not form stable pi-pi multiple bond because they have larger orbital size for NP orbitals. Hence, they do not give rise to an effective lateral orbital overlap. The second one is nitrogen lacks of catenation tendency because of weakness of N single bond. This is attributed to the lone pair repulsion between nitrogen atoms. The other element, however, forms stable single bond because of their large atomic size. Thus, longer bond length will reduce the lone pair repulsion. Next, nitrogen has a maximum covalency of 4 only, since total 4 valent orbital 1 to S and 3 to P are available for bonding. But for the heavier element, they have vacant d orbitals in the outermost shell, which can be used for bonding. So that is why they can expand their covalency up to 6. Now I'm going to explain about chemical reactivity of group 15 element towards hydrogen, oxygen, halogen, and also metals. But let us start with reactivity towards hydrogen. So when group 15 element react with hydrogen, they will form hydride. These are the list of the hydride formed by group 15 element with hydrogen. So let's see the properties of this hydride. But I want to clarify something. When we talk about chemical properties of group 15 element, we already seen the elements such as nitrogen, phosphorus, arsenic, antimony, and also bismuth, how their melting point change, and also how their boiling point differ from each other. But now, we are going to see the chemical properties of their compound, which are hydride. So, as you can see here, the atomic size increases going down the group. So when element size increases, this will cause the bond length between central atom, which is group 15 element, and hydrogen to increase. Thus, the strength decreases because it is much easier to break the bond. Based on this strength, we can talk about trend of other properties as well. So the first one, when the strand become weaker, it is obviously easier to break the bond. So less energy is needed. So that's why bond dissociation enthalpy decreases. Bond dissociation enthalpy is the amount of the energy required to break the bond. Okay, stability of hydride decreases because when you can break the bond easily, then it shows how unstable the element. The third one is the reducing character. Reducing character is the tendency to liberate hydrogen. This can reduce other species. So as you know, stability decreased going down the group. So what will happen is that the ability to release hydrogen decreases. So that's why the reducing character increases. Bismuthine is the strongest reducing agent. Okay, the next one is basicity. So basicity, or known as basic nature, decreases going down the group. All hydride are Lewis bases because lone pair of electron is present. Lewis bases means those species that can give electron. The reason why basicity decreases going down the group is because when atomic size increases, electron density decreases. Let's take ammonia as an example. As you know, a central atom of ammonia is nitrogen, and nitrogen is very small in size and has a very high electron density. All the electron density is consolidated in a small space. So its electron releasing tendency is at maximum. Going down the group, there is a gradual increase in the atomic size. So the electron density on the central atom decreases as the size is getting bigger and bigger. So the electron density will be spreading around the surrounding, not like ammonia, which the electron density is consolidated in a small space. So the next one is boiling point increases going down the group because of the strong magnitude of van der Waals force. But boiling point of ammonia is higher than pH3 and also ASH3. This is because of ammonia has intermolecular hydrogen bonding. Nitrogen become more electronegative as it gets a partial negative charge, and hydrogen gets a partial positive charge. So they tend to form intermolecular hydrogen bonding with other molecules of ammonia. So we need more energy to break the bond. So that's why boiling point of ammonia increases. So when group 50 element react with oxygen, they will form two types of oxide, which are trioxide and also pentoxide. Regarding oxide, you should know the acidic strength. So to understand and arrange this oxide in order of their acidic strength, you should know some basic properties, which are oxide of non-metal will become acidic. Oxide of metalloid will become amphoteric. Amphoteric means it show both acidic and also basic character. And oxide of metal will become basic. So among oxide of different element, the higher the electronegativity of the element, the higher the acidity of the oxide. The second one, among the oxide of the same element, the higher the oxidation state, the higher the acidity strength. So let us try to arrange this oxide in the order of increasing acidic strength. So the first one, acidic strength of oxide of nitrogen. So N2O and NO is natural in nature. So following what I explained just now, when you compare the oxide of the same element, the higher the oxidation state, the higher the acidic strength. So that is why N2O5 is higher than N2O4. The second one is acidic strength of trioxide. S4O6 and SB4O6 is amphoteric in nature. When we compare the oxide of different elements, the greater the electronegativity, the greater the acidic strength. As you know, the electronegativity decreases going down the group. So that's why B4O6 is higher than N2O3. When acidic strength decreases, the basic strength will increase for the trioxide. Thus, Bi2O3 become basic in nature. The third one is acidic strength of pentoxide. It is just the same as the trioxide. Now we are moving to the reactivity of group 15 element towards halogen. So when group 15 element denote as E react with halogen, which denote as X, they will form two types of halide, which are trihalide and also pentahalide. Nitrogen does not form pentahalide due to the non-availability of the orbitals. Okay, the electronic configuration of nitrogen is 1s2, 2s2, and also 2p3. So nitrogen does not have the orbital in the valence electron. Thus, nitrogen cannot extend its covalency beyond 4. Pentahalide of bismuth does not exist because of the strong inert pair effect, as electron in s orbital is not available for bond formation. Phosphorus is not capable of forming pentahalide with GPI5 because phosphorus cannot accommodate 5 atoms of iodine as they are bigger in size. So as you can see here, iodine is much bigger than the phosphorus. You can refer to the atomic weight here. Pentahalide are also more covalent than trihalide. They cannot form ionic compound because it is more difficult to lose 5 electrons to form E positive 5 ion. So they share electron. So all trihalides are stable except nitrogen. Nitrogen trihalides are unstable because of the large difference in size of nitrogen and halogen atom. Nitrogen is very small in size, and size of halogen atoms are getting bigger and bigger. Only NF3 is stable because both nitrogen and also fluorine are small in size. As you can see here, atomic weight of nitrogen is 14 and atomic weight of fluorine is 19. So they can have a strong bond formation between nitrogen and also fluorine. All trihalides are covalent except BIF3 because it is ionic in nature. So the last one is the reactivity of group 15 element towards metal. So when the group 15 element react with metal, they will form binary compounds. All of the group 15 element exhibit -3 oxidation state in this binary compound. As you can see here, for example, calcium nitride and also calcium phosphide. So yeah, that is all from me. I will pass to the next person to explain further about group 16 element. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and good day I bid to everyone. I am Aina Nabiha binti Muhammad and also with me are Muhammad Fakrullah bin Muhammad Rohaizan and Nur Erdina binti Muhammad Haiza. So today we are going to present about group 16 of periodic tables or also known as P block element. So before we go more deeply into group 16 of periodic tables, so let's see the overview of this group. So in this group, it consists 5 elements which are oxygen, sulfur, selenium, tellurium, and polonium. Oxygen, like nitrogen, occurs as a low boiling diatomic gas, oxygen. Sulfur, like phosphorus, occurs as a polyatomic molecular solid. Selenium, like arsenite, occurs as a grey metalloid. Tellurium, like antimony, display network covalent bonding. And polonium, like bismuth, has a metallic crystal structure. So p-block element or 6A elements consists of the elements of oxygen, sulfur, selenium, tellurium, and polonium. The electron configuration for this group is Ns2 and P4. Oxygen is a diatomic gas while sulfur, selenium, and tellurium are octatomic, which are S8, Se8, and Te8 molecules, which have a ring structure. Oxygen and sulfur are non-metal, as elements increasingly non-metallic towards the right-hand side of periodic table. Selenium and tellurium are semi-metallic. Polonium exhibits metallic characters. Oxygen and sulfur have the most significant chemistry in this group, and oxygens are more reactive compared to the other elements of this group. So next is the general trend of group 16 or 6A element. So the metallic properties increase down the group, means starting from the oxygens to the uh, polonium, the metallic properties increase. So the melting and boiling point show the rising trend characteristic of non-metals followed by the drop at the metallic polonium. So you can see from this table, the melting point and the boiling point keep increasing from oxygen to the tellurium, and it will drop at the polonium. So density and atomic radius and ionic radius all increase down the group. And the ionization energy for this group decrease down the group. So next is the oxidation state for the group 16 element. The most common oxidation state is -2. Sulfur can exist at a positive or +4 and +6 state. Oxidation state that possible for selenium, tellurium, and polonium are +2, +4, and +6. The stability of the -2 and +6 oxidation state decreased down the group, while that of the +4 states increased. The stability of -2 oxidation state decreased down the group due to the increase of atomic size and decrease of the electronegativity, and also the stability of positive 6 oxidation state decreased and +4 oxidation state increased due to the inert pair effect. Oxygen does not show positive 6 oxidation state due to the absence of the d orbital. Next is the reactivity of the group 16 with hydrogen. All group 16 form hydrides of type H2. X here represent the group 16 element. So group 16 have a band shape. Hydride bond angles decrease and bond length increase down the group. Order of the bond angle from H2O larger than H2S, larger than H2SE, larger than H2TE, larger than H2PO. So in conclusion, the bond angle of H2O is the largest, while H2PO is the smallest. So the angle of H at H bond angle in water is 104.311 degree, but in other hydride it almost equals to 90 degree. In water in H2O, oxygen is involved in sp3 hybridization, but in other hydride pure, p orbital are participate in the bonding. Oxygen and sulfur form less stable polyoxide and polysulfides like H2O2, H2S2, H2SN. So the N represent to the numbers starting from 2 to 10. So H2O and H2O2 can be formed hydrogen bonding and therefore have high melting and boiling point than other H2S compound. So reaction with hydrogen acidic nature starting from the H2O to the H2TE, it will decrease. So it means H2O has the lowest acidic nature and H2TE has the highest acidic nature. This is because the hydrogen to the group 16 element bond length increase down the group. Therefore, the bond dissociation energy down the group. For H2O is also a liquid, but the hydrides of the other 6A element are gas. This is because strong hydrogen bond is present in water and due to the small size and high electronegativity of oxygen. So next, we will see the reactivity with the oxygen. The other element of the group are oxidized by the oxygen. So as you can see from this chemical equation, the group 16 element, which is here represented as S, will react with oxygen and will produce SO2. So X here represent the sulfur, selenium, tellurium, and the polonium. So it depends on what element that are going to oxidize by the oxygen. So 6A group element form two types of oxide. First is dioxide, which is SO2, and the second one is trioxide, is SO3. So acidity decreased down the group, and sulfur dioxide is a gas, while selenium dioxide is solid. This is because selenium oxide has a chain polymeric structure, while sulfur dioxide form isolated unit. So the sulfur dioxide is oxide, and the product of sulfur dioxide is produced in the production of sulfuric acid. So as you can see from this under chemical reaction, down here, so 2 sulfur dioxide will react with the oxygen, will produce 2 SO3. So these SO3 are used in the sulfuric acid production. So type of oxide can be divided into 4 types. First is acidic oxide, which is non-metallic oxide, are acidic in the nature. So here, as you can see from this chemical equation, so the SO2 will react with the water to produce H2SO3, which is sulfuric acid. The second type is basic oxide. So it is a metallic oxide that are basic in the nature and is dissolved in water and form a base. So as we can see from this chemical equation, Na2O will react with the water and will produce natrium hydroxide or not NaOH with the water. So NaOH here is a base. The third type of oxide is amphoteric oxide. It is both acidic and basic oxide. So as you can see from this chemical equation, La2O3 will react with 6 HCl to produce 2 AlCl3 plus 3 H2O. So the second one is Al2O3 will react with 6 NaOH And also with 3 molecules of water to produce 2 Na3AlOH6. So both are produced a salt product. So the fourth type is neutral oxide. So these oxides are neither acidic or basic. So it means it is a natural. It is neutral. So for example, it's carbon monoxide, nitrogen oxide, and nitrogen 2 oxide. So next we will see the reactivity of with halogen. So halides are formed by direct combination. For example, as you can see from this chemical equation, so X which is represent the sulfur, selenium, and also the tellurium will react with any halogen that represent as Y here, which is Y2. So example of Y here is fluoride and fluorine and chlorine. So it will produce as halides. So the 6A group element form monohalides, dihalides, tetrahalides, and hexahalides. The oxidation state of sulfur, selenium, and tellurium is monohalide is +1, in dihalide is +2, and in tetrahalide is +4, and in hexahalides is +6. Hexafluorides are the only stable halides which are gas and have sp3d2 hybridization and octahedral structure. So this structure and reactivity depends on the size of the central atom and the surrounding halogens. The larger central atoms, the more larger central atom, the halides become more stable. The pattern is related to the effects of electron repulsion due to the crowding of lone pairs and halogen atoms around the central. This is opposite to the previously observed bonding patterns. As bond strength decrease, the bond length increase. The stability of halides decrease in the others. As you can see here, the stability for fluoride is the highest, while for iodide is the lowest. So this is because the SY bond or the bond between the group A element, group 16A element, and the halide bond length is increased in size.
Hi, my name is Nuridina binti Muhammad Haiza and my metric number is 207921. Today I'll be continuing the presentation of our SCL, which is our title is Group 16 on the allotropes in the oxygen family. Oxygen has two allotropes, O2, which is essential in life, and O3, which also known as ozone, that is poisonous. Sulfur has more than 10 different forms due to the ability of sulfur to catenate. Catenation is the bonding of atoms of the same element in series, called chain. The SS bond length and bond angles may vary greatly. For example, yellow rhombic, the alpha sulfuric and monoclinic beta sulfur. At 369 Kelvin, both forms are stable. It is called transition temperature. Both of them have octasulfur molecules. The ring is puckered and has a crown shape. Selenium has several allotropes, some consisting of crown-shaped octaselenium molecules. Oxygen. Oxygen is a gas at room temperature and 1 atmosphere pressure. It is colorless and tasteless. It is the most abundant element in the earth crust and the most abundant element in seawater. It's second to nitrogen as the most abundant in the atmosphere. There are many commercial uses for oxygen gas. It is used in manufacture of iron, steel, and other chemical manufacturing. It is also used in water treatment as an oxidizer in rocket fuel for medicine purposes and in petroleum refining. It exists as two allotropes like I've mentioned previously, the O2 and O3. Its primary oxidation states are -2, -1, 0, and -1/2 in O2 minus. When oxygen reacts with metals, it forms oxides that are mostly ionic in nature. It's rarely featured as the central atom in a structure and can never have more than 4 elements bonded to it due to its small size and its inability to create an expanded valence shell. When it reacts with hydrogen, it forms water, which is extensively hydrogen bonded, has a large dipole moment, and is considered an universal solvent. Sulfur. Sulfur is a solid at room temperature and 1 atm pressure. It's the 16th most abundant element in Earth crust. It exists in a variety of forms naturally, including elemental sulfur, sulfides, sulfates, and organosulfur compounds. Sulfur is very unique in its ability to form a wide range of allotropes, more than any other element in the periodic table. At room temperature, the sulfur molecule is a crown-shaped ring of 8 atoms. The most stable S allotrope is orthorhombic alpha octasulfur, which consists of cyclooctasulfur. The most common state for sulfur to be in is the solid octasulfur ring. Sulfur exists in the gaseous form in 5 different forms: the S-sulfur, disulfur, tetrasulfur, hexasulfur, and octasulfur. In order for sulfur to get to these states, one must apply a sufficient amount of heat. Two very common oxides of sulfur are sulfur dioxides, SO2, and sulfur trioxides, SO3. These two compounds are used in the production of sulfuric acid. Sulfur also exhibits a wide range of oxidation states, with values ranging from -2 to +6. It is often the central ion in a compound and can easily hold up to 6 atoms around itself, compared to the oxygen. And when in the presence of hydrogen, it forms the compound H2S, which is a poisonous gas without hydrogen bonds and a very small dipole moment. This reaction with hydrogen epitomizes how different oxygen and sulfur act despite their common valence electron configuration and common non-metallic properties. Here are the common compounds of sulfur with various oxidation states. When the oxidation state of sulfur is +6, the compounds are like SO3, H2SO4, which is the sulfuric acid, SO4 2-, and SF6. When the oxidation state at +4, the compounds are like SO2, HSO3-, SO3 2-, and SF4. When the oxidation state +2, the compound is SCL2. When the oxidation state is 0, S8, and all other form of elemental sulfur. And -2 oxidation state gives H2S and S2- for the ensemble of the compounds. Contrast in the chemistry of oxygen and sulfur. Oxygen is limited to a maximum of 4 covalent bonds, whereas sulfur forms up to 6 covalent bonds. For example, oxygen forms only one normal oxide with fluorine, OF2, whereas sulfur forms several compounds with fluorine, including SF6. The oxygen-oxygen double bond is much stronger than the oxygen-oxygen single bond. For sulfur and the other members of the group, the energy of 2 single bonds is greater than that of 1 double bond. For this reason, multiple bonding is only common for oxygen. Here in the table, we can see the oxygen-oxygen single bond, the bond energy gives 142 kJ per mole, while the sulfur-sulfur single bond is 268 kJ per mole. For oxygen-oxygen double bond, the bond energy is 494 kJ per mole, while sulfur double bond is 425 kJ per mole. We can see here that the double bond for oxygen-oxygen is way much higher than oxygen single bond. Same goes to sulfur, but to be compared, sulfur and oxygen, the difference of bond energy from single bond to double bond for oxygen is way much higher than sulfur. Next, oxygen prefers to bond to other elements rather than to itself. For example, the covalent bond to hydrogen is very, very strong due to the weakness of the oxygen-oxygen single bond compared to its bond to other elements. Conversely, the sulfur tends to stabilize its compounds by catenation. The sulfur-sulfur single bond energy is only slightly lower than the energy of sulfur's bond to other elements. Here in the table, you can see the single bond of oxygen and chlorine. The bond energy is 218, which is higher than single bond of oxygen-oxygen. But for sulfur bond with chlorine in single bond, the bond energy is 271, just slightly higher than sulfur-sulfur single bond. For oxygen and hydrogen single bond, the bond energy is 459, which is high. And for sulfur and hydrogen single bond, the bond energy is 363. We can say that oxygen and hydrogen single bond is higher compared to sulfur and hydrogen single bond. Highlights of sulfur chemistry. The ozone, O3. Ozone is a good oxidizing agent. It can be used as a substitute for chlorine in purifying drinking water without giving the water an oat taste. However, because of its unstable nature, it disappears and leaves the water unprotected from bacteria. So, if we want to substitute chlorine to purify drinking water, we must add the antibacteria in the water to make sure that it is free from live bacteria. Ozone at the very high altitudes in the atmosphere is responsible for protecting the Earth's surface from ultraviolet radiation. However, at lower altitudes, it becomes a major component of smog, which is a type of air pollution. Thank you, that's all from me, and my friend will be continuing the presentation.
Assalamualaikum warahmatullahi wabarakatuh to all my fellow friends and my beloved lecturer. My name is Muhammad Fakullah. My matrix number of 207689. And now I would like to continue this presentation regarding the sulfur chemistry, which is ozone. So basically, ozone is a good oxidizing agent. It can be used as a substitute for chlorine in purifying drinking water without giving the water an oat taste. However, because of its unstable nature, it disappears and leave the water unprotected from bacteria. Ozone at a very high altitude in the atmosphere is responsible for protecting the Earth's surface from ultraviolet radiation. However, at lower altitude, it becomes a major component of smoke. And the preparation of ozone, it is prepared by passing silent electric discharge to pure and dry oxygen. Then until 15% of oxygen convert to ozone. So basically, at this part, we can see the 3 mole of oxygen are converting to 2 mole of ozone, which need the energy 142 kilojoule per mole. And the structure of ozone has angular structure, and both double bond are equal length due to resonance. So at the bottom side of this presentation slide, we can see the resonance of the ozone molecule. And sulfur from 2 important oxides, which is sulfur dioxide, has in its +4 oxidation state. It is a colorless choking gas and form when sulfur H2S or metal sulfide burn in air, while sulfur trioxide has S in the +6 oxidation state. Two resonance structure for sulfur trioxide. The sulfur dioxide molecule is a band molecule. So at this part, we can see the 3 resonance for sulfur trioxide molecule. And for sulfur dioxide, sulfur burn in air to form sulfur dioxide. And the property for sulfur dioxide, it is a gas. It is also a colorless gas and poisonous gas. The sulfur dioxide in our air come from approximate 7 to the power of 10 kilogram decomposition of vegetation and volcanic emission. Approximation 1 to the power of 11 kilogram naturally occurring H2S, which is oxidized to sulfur dioxide by oxygen. and approximate 1.5 to the power of 11 kilogram industry and transportation, which is electricity plant. And sulfur can act as either oxidizing agent or an reducing agent. Sulfur dioxide is starting material for making sulfur trioxide. The sulfur trioxide is then used to make sulfuric acid. So at this bottom side, the presentation slide, we can see where 2 mole of sulfur dioxide we combine with oxygens to produce 2 mole of sulfur trioxide. And the uses for sulfur dioxide is for refrigerator, preserve dry food, bleach for textile and fur, and of course to produce sulfuric acid. And sulfur form two important oxo acid, which is sulfurous acid. H2SO3 is a weak acid with 2 acid proton, and the other acid is sulfuric acid, which is H2SO4, which is a strong acid, and it is important industrial chemical. It is an excellent dehydrating agent. So at this side, we can see the Lewis structure for sulfurous acid, which is H2SO3. And the other form of sulfur in the form of acid is sulfuric acid, which is H2SO4. H2SO4 is the most heavily produced inorganic chemical worldwide. About 2/3 of sulfuric acid produced goes into manufacturing. In the uses of sulfuric acid, it is widely used in industry for the production of fertilizer, petrochemical, and detergent. And 3 important chemical properties of H2SO4 are: it is a strong bronze-free acid, and it is a dehydrating agent, and the most important thing, the sulfuric acid is an oxidizing agent. Next is sulfur halide. Sulfur react directly with all the halogen except iodine. And the first form of the sulfur halide is sulfur hexafluoride, which is SF6. Sulfur reacts spontaneously in fluorine and burn brightly to give SF6. Despite its high oxidation number +6, it is not a good oxidizing agent. It is a good insulator in air and is used in switch on high voltage power line. And the properties for sulfur hexafluoride is it is a colorless gas, is also thermally stable and non-toxic gas. And for the group 6A, which are group 16 element, they consist of oxygen, sulfur, selenium, tellurium, and polonium. Where oxygen most likely like nitrogen, where it is occur as a low boiling diatomic gas. And sulfur are mostly like phosphorus, where occur as polyatomic molecular solid. And selenium are more likely arsenic, commonly occur as a gray metalloid. And tellurium is like antinomy, where it display network covalent bonding. And lastly, polonium, which is act like a bismuth, which has a metallic crystal structure. And I think that's all from me. And thank you.